Welcome. This is a time series analysis course. My name is Nicoleta Sturban. I'm Associate Professor in the Stuart School of Industrial and System Engineering. This lecture is on modeling heteroscedasticity, and in this lesson I will illustrate the implementation of the GARCH model with a data example. We'll return to the data example in which we model the stock price of PDCE Energy, the company that is a producer of crude oil and natural gas in the United States. Daily stock prices for more than 10 years of data, starting with January 2007, are considered in this data example. In the previous analysis of the PDCE price return, we first fitted an ARMA model with the selected orders 5 and 6, then applied an ARCH model to the residual process. We also compare it to a joint ARMA-ARCH model. Here, we consider modeling the return price using a joint ARMA-GARCH model. We fix the ARMA orders to be selected, the selected orders 5 and 6, using the AIC approach from the previous lesson. We'll next select the order of the GARCH model. To select the orders, we loop over all combinations of orders M and N with values between 0 and 3. Note that we consider somewhat smaller orders for GARCH than we use for ARMA modeling, since a small GARCH model commonly is sufficient in modeling the volatility. In this implementation, I first define the model's specifics through the uGARCH spec R function. The model specifics are as follows. The ARMA orders are 5 and 6. The GARCH orders are M and N. We consider the mean to be non-zero, and we assume the t-distribution instead of normal distribution through the specification, the option distribution dot model. Then the model is fitted using the uGARCH fit with the formulation specified by the specifics in a previous in a uGARCH spec. Note that this is yet another R function or another R implementation that can be used to fit a joint ARMA-GARCH model. This R function is available. The R functions used on this slide are available in RUGARCH library. This implementation, this library, this is one, if not the most recent implementation of the ARMA-GARCH model. It provides many more modeling options for modeling the conditional mean and the conditional variance jointly, as I will show in the rest of the lessons of this lecture. Instead of using the AIC, I now use the BIC, since BIC prefers smaller, less complex models. And thus, we fit, and this is important because we fit an ARCH-GARCH joint model, which is already very complex. The final order will keep the values of N and M because BIC does not get smaller for larger values of M and N beyond the selected orders. The selected orders in this implementation are the AR order or M equal to 1 and the MA order or N equal to 2. However, when fitting ARMA-GARCH simultaneously, jointly, we should determine both the ARMA and the GARCH orders jointly. If the process is indeed well approximated by an ARMA-GARCH model, then considering the conditional mean model ARMA while neglecting the conditional variance model GARCH, as we did in the first implementation, will lead to inefficient estimators. Similarly, when considering the conditional variance model, you should not neglect the model for the conditional mean. This is because neither the conditional mean model nor the conditional variance model can be estimated consistently if taken separately. Joint estimation will typically be more efficient and this is why it is preferred. Unfortunately, the task of jointly determining the ARMA and GARCH orders is difficult, so it will require fitting many more models. For example, if we assume orders from 0 to 5 for both orders of the ARMA, the AR and MA orders for the ARMA for the conditional mean, and orders from 0 to 3 for both orders of the GARCH for the conditional mean, we would have to fit 576 models, ARMA-GARCH models. Fitting an ARMA gauge model is computationally expensive, and thus, without distributed computing, fitting all models will take more than a day of computation time. Alternatively, we can select the order for ARMA and gauge separately, but refine the order selection through multiple refinements. Thus here, we'll apply order selection for ARMA given the selected orders of gauge in the previous slide. That is, we fixed the orders for the gauge to be equal to 1 and 2, and now select the orders P and Q for ARMA. I apply the same code as in the previous slide, except that now I'm varying the orders for ARMA. The selected orders for ARMA are 0 and 0. That is, the conditional mean does not depend on time. Next, I refine the orders of gauge assuming an ARMA 00 as selected in the previous slide. The selected gauge is the classic gauge 11 commonly used to model stock price returns. Let's now compare the three models. We have the three models are as follows. The the joint model, where the ARMA orders are 5 and 6 and the gauge model are 1 and 2. The second model is when the ARMA orders are 0 and 0 and gauge orders are 1 and 2. The third model, where the ARMA orders are 0 and 0 and the gauge orders are 1 and 1. We'll compare with respect to the AIC, BIC, and other information criteria. We can compute the information criteria of a model estimated using the U-gauge fit from the library RU-gauge using the info criteria command, R function. This function it applies only to models fitted with the U-gauge fit from the RU-gauge library. The output is here. The first two values are the Akai-Iki information criteria, or AIC, and for the Bayesian information criteria, or BIC. For example, the values across, in this example, the values across the 4, 5 criteria are very similar for the three models. Since we prefer less complex models, thus we would choose the last model, where we have an ARMA with orders 0, 0 and a gauge with orders 1 and 1. These are the ACF plots for the residuals and the squared residuals of the selected model, of the less complex model. Based on this plot, the ACF of the residuals resembles the ACF plot of the residuals resembles the ACF of a white noise. However, this is not the case for the squared residuals, suggesting that a higher order gauge model may be considered. The R code on this slide is for obtaining the predictions for the conditional mean and for the conditional variance, or for the so-called volatility. The prediction is performed one lag ahead on a rolling basis, starting beginning of 2017. The code on the slide is for the first model, but I applied the code to obtain the predictions using the other two models also. The output of the model consists of forecasts for the return price, for the conditional mean, and the conditional variance. These are the prediction accuracy measures for the conditional mean based on the three models. Model 1 performs best across all measures. This is the R code we can use to compare the predictions to the observed data using a visual display. From this R code, we see that the predictions for the conditional mean are close to the 0 line. This is because in this example, the volatility predominates over the conditional mean. In this plot, in this code, I'm contrasting the squared time series with the predictions for the conditional variance. And this is the plot. The predictions capture some of the volatility. However, all models consider underpredict the conditional variance, the volatility. In summary, in this data example, I illustrated the implementation of the GARCH model with the data example. Thank you.